All right, what's up everyone? This is going to be my explanation for the first subtask of problem division 2E / division 1C. And it's called Converging Array. So I'll just say this is 1C / 2E, and this is the easy version. Now the problem says this is the easy version, but I think the problem is actually pretty difficult, especially for a 1C position. So if you are completely lost, then that is completely fine. I was lost too when I first read the problem, but I think I understand it well enough to where I can explain it, and hopefully you find it useful. Now, if you find this explanation confusing whatsoever, do look at the official editorial, because it's likely that they explain the solution a little bit better than I do, but I will try my best regardless. So, the first thing to notice is that these operations that we're given, so like we're given operations like a at I is equal to min of a at I, and a at I plus a at I plus 1 minus b at I over 2. And we're also given a at I plus 1 is equal to the max of a at I plus 1 and a at I plus a at I plus 1 plus b at I over 2. So you might look at this and you're thinking, what the hell? This looks awful. And I 100% agree with you. This looks terrible. Like, I can't even begin to think about what on earth this function does. So maybe this is the first thing we should do. We should think about what exactly does this operation do to the elements of a at I. And I think the best way to figure this out is to just do an operation. So let's do this. Let's assume a at I was equal to 2, a at I plus 1 was equal to 5, and b at I was equal to 5. Okay? So by doing an operation, what we do is we essentially set a at I to equal to the min of itself, which is equal to 2 currently, and we simultaneously do these operations. So it's essentially 2 plus 5 minus 5, because it's a at I plus array at I plus a at I plus 1 minus b at I over 2. And so then, while at the same time we do a at I plus 1 is equal to the max of itself, which is equal to 5, and then we do a at I plus 1 plus b at I, so it's 2 plus 5 plus 5, all over 2. And so this is equal to 2 plus 5, which is 7, minus 5, which is 2, over 2, which is equal to 1. The minimum of 1 and 2 is equal to 1. And so a at I becomes 1. While at the same time, 2 plus 5 plus 5 is equal to 12, 12 over 2 is equal to 6, and the maximum of 5 and 6 is equal to 6. So a at I plus 1 becomes 6. Okay? So this 2 turns into a 1, and this 5 turns into a 6. Okay? I think the one thing that might be helpful to do is, what if we repeat this operation again? So if we do a at I is equal to the minimum of itself, 2, and then we do 1 plus 6 minus 5 over 2, and then we do a at I plus 1 equal to the max of itself, which is equal to 6, and then 1 plus 6 plus 5 over 2. This is equal to 2 over here, because 7 minus 5 over 2, 7 minus 5 is equal to 2, 2 over 2 is equal to this. Is this correct? Oh wait, no, it's a minimum of 1 in itself. Yeah, my bad. So yeah, and so that's equal to 1. And so the minimum of 1 and 1 is equal to 1. And then over here, 1 plus 6 plus 5 is equal to 12, over 2 is equal to 6, and the maximum of 6 and 6 is equal to 6. Okay, this is kind of interesting. We notice that if we do operations on AI and AI plus 1, and it changes to some sort of value, if we repeat this operation right after we did this operation, it's not going to do anything to our array. So what I mean by that is, if we do an operation on I and I plus 1, if directly after we do an operation on I and I plus 1 again, this will do nothing. So this is one step towards helping us kind of understand what exactly this operation is doing. And I think to fully understand what this operation does, let's check one more set of values. So in this case, I will do this. I will do a at I equal to 3. A at I plus 1 is equal to 10, and B at I is equal to 5. So let's try doing an operation on A at I and A at I plus 1. So A at I is going to be equal to the min of itself, which is currently equal to 3. And then we have 3 plus 10 minus 5 over 2. So 3 plus 10 minus 5 over 2. And we have A at I plus 1, which is now equal to the maximum of itself, which is equal to 10. And then it's 3 plus 10 plus 5 all over 2. So this quantity over here is equal to 13 minus 5, which is equal to 8. 8 over 2 is equal to 4. And then the minimum of 3 and 4 is equal to 3. So this will be assigned a value of 3. And so likewise over here, 3 plus 10 plus 5 is equal to 18. 18 over 2 is equal to 9. And the maximum of 10 and 9 is equal to 9. Okay, so this is, no, my bad. The maximum of 10 and 9 is now equal to 10. So what is interesting about this is that doing this operation did not end up changing these values of A at I plus 1 at all. It literally did nothing at all. And so you might want to realize something. This value was equal to 4. This value over here was equal to 9. What this function is doing is the following. If the difference of A at I plus 1 minus A at I, if this difference is strictly less than B at I, then it assigns the values of A at I and AI plus 1 equally, so that the difference becomes B at I. Right? And so this is what this operation will do to this, and in this case, it will essentially figure out how much you need to change the value of A at I, how much you need to decrease A at I, how much you need to increase A at I plus 1, such that the difference goes from strictly some value that's less than B at I to some value that's equal to B of I. And it adds on, and the deltas are essentially the same value. So we know that if this condition is held, then this will happen. And likewise, we know that if A at I plus 1 minus array at I, if it's greater than or equal to B at I, then this will do absolutely nothing to our current values. If we do an operation on index I, then nothing changes. So this is a much easier way to visualize this problem, or not the problem, but the operations. Because now, instead of having to deal with these disgusting minimum and maximum formulas and all this arithmetic, we can simply just think of an operation as we take these differences and we just expand them to be as big as B at I, assuming that this difference isn't already B of I or bigger. Okay, so this is great. This is one critical observation that we need to make. Okay, so now we need to think of it like this. Let's assume that we have some array that's I don't know. I'll just use variable names. So just A at 1, A at 2, A at 3, A at 4, and A at 5. And then our B array is just equal to B at 1, B at 2, B at 3, and B at 4. So let's consider doing some operations on a prefix of this initial array. And the reason why we want to think of doing operations on the prefix is because the value that we care about in the end is f at A and B. And this is literally just equal to the first, and this is just equal to A at 1 after operations are done, and after all these values converge to the limit. So after operations, I'll just abbreviate it like this. So because we only care about the first element and what that value converges to, it would make sense to think of doing operations on a prefix. So let's notice that if all the operations that we do are on index I, and for example, let's say we never do an operation beyond index 2. So we do an operation on index 2, and it affects index, it can also affect index at 2 plus 1, which is equal to 3. But what this means is that we can never affect this value of array at 4. And the reason why is because we essentially only change adjacent elements in one move. And so if we can never make this adjacent change between across 3 and 4, like the values located at index 3 and 4, then we can never, then we can never affect the sum, like between across this like cut. Okay, let me reword that. Any operation such that, in this case, if the rightmost operation we do will affect 2 and 3, then the sum of a at 1, 2, and 3 stays constant. Well, stays the same relative, and the sum of a at 4 plus a at 5 will also stay the same. And the reason why is because we can never do a move across a at 3 and array at 4, because we assume over here we would never do that type of move. And if we assume we never do this type of move, then what that means is that any values like in this current segment can never flood over to this like subarray over here. So something like this. So this is what happens if we consider only doing moves in some prefix of the array, right? And then because this first element will be located in whatever the first subarray we split it into is, then we can think of it like that. But this isn't necessarily, or it's not always necessarily true to just randomly pick some prefix and just like assign all these values to like stabilize. And the reason why is this. The reason why is actually really simple. It's because it's possible that if we did a move at a at 3 and a at 4, and I guess the corresponding index is b at 3, it's possible that these values do change, right? And like we mentioned earlier, the only time doing an operation on this pair, like will change the values is if a at 4 minus a at 3 is strictly less than b at 3. Because if it was strictly less than b at 3, then they would change the values such that a at 4 minus a at 3 will be equal to b at 3. And if we change the values of a at 4, a at 3, then some number will be exchanged from here to here. And these subarrays will essentially merge into one like bucket. And so it'll look something like this. So let's assume that we don't want to have like this exchange ever happen. What is the only time in which we can do an operation on a at 3 and a at 4 and not have values change whatsoever? So in other words, we want to assign a at 3 and a at 4 some values such that some quantity in this subarray will never leak over to the subarray over here. Like everything in here is isolated, everything in here is isolated. And if you were paying attention, you might realize that we can actually ensure this happens if the initial values of a at 4 and a at 3, if a difference of these initial values is strictly greater than or equal to b at 3, because doing an operation on these set of values will do nothing to our array whatsoever. So this is the most important observation to make. Or I guess one of the big important observations to make. So because of this observation, we can theoretically create this cutoff point wherever we want, because we can assign like some value to a at 3, some value to a at 4. And if it's a sufficient distance from b at 3 or a sufficient difference, then we can consider a prefix as its own. So let's assume that we can do some moves in the prefix, because keep in mind that in the prefix we choose, it's like for example, if a at j plus 1 minus array at j was inside of our prefix, if the initial values satisfy this equation, then this value can never be in our initial prefix. And the reason why is because if, for example, like this was a at j and this was a at j plus 1, we can never exchange a quantity between these two moves, meaning that a at j and a at j plus 1 belong to different segments. And if they belong in different segments, they can't belong in the same prefix. So that's why you have to assume that all like pairs inside of a current prefix that we're considering, all of them have to satisfy this. Okay? So let's assume that they satisfy that. And then we do like some set of operations. Well, one, we know that doing any operation inside of its prefix will never change the sum of a prefix. And the reason why is because, well, we know that if we expand like the difference between any two numbers, they both expand in the same amount. So if, for example, if a at I decreases by x, then array at I plus 1 will increase by x. And so the total like delta of the prefix will just be equal to 0. So, for example, let's just say we were to do some moves on prefix a at 1, a at 2, a at 3, and then a at 4. And then our current b values are like b at 1, b at 2, b at 3, whatever. So if we assume that all these differences are strictly less than the current b value, so in this case, if a at 2 minus a at 1 is strictly less than b at 1, a at 3 minus a at 2 is strictly less than b at 2, and a at 4 minus a at 3 is strictly less than b at 3, then doing these operations will, in fact, affect our answer and will like change some elements in this array. So how exactly will they change? Well, they'll change like this. After some like process we simulate, because we know that like whatever, like I'm just using these arrows to like represent like some process. Like it doesn't really matter like what order we do them in or like how many like turns. I guess it does matter how many turns, but like after infinitely many number of turns, we realize that obviously we have to get to a point where if we do an operation on any index, then those values will not change, because if they do change, then that means that they haven't converged yet. So do you remember when we make a move, what is a condition that has to be held in order for those values to not change? Well, it has to be when array at I plus 1 minus array at I is greater than or equal to b at I. But because we know that initially, like these differences are strictly less than b at I, after we do a move on them, they can only be equal to b at I, because that's what a move does. If the difference between like adjacent values is strictly less than b at I, then it sets the difference equal to b at I. So we make this move, and we know that the final array will look something like this. So like, let's just assume that our final array looks like f of 1, should I use f? I'll use x. So I'll define x as, so if I do x at 1, x at 2, x at 3, and x at 4, and x array is defined as the array A. It's like the A array when it converges. Okay? And so we know that by the logic that we mentioned earlier, we know that x at 2 minus x1 has to equal to b at 1, x at 3 minus x at 2 is equal to b at 2, and then x at 4 minus x at 3 is equal to b at 3. Because that's the definition for this array to converge to these values. So because we know all of these like definitions, we can actually like, instead of having x1, x2, x3, x4, like so on, we can change x2 to be equal to x at 1 plus b at 1. We can change x at 3 to be equal to x at 1 plus b at 1 plus b at 2. And then we can change x at 4 to be x at 1 plus b at 1 plus b at 2 plus b at 3. Okay? So this is what the final array will look like. And then x1 is just like some value of x that we converge to. So the important thing about x1 is that x1 always equals to a at 1 after it converges. And as a matter of fact, x1 is equal to f at a and b. So this x1 is actually the value that we want to consider in the end. And so, in other words, what this means is that we need to make sure that if we want to count like this array towards our answer, then we need to make sure that x1 is strictly greater than the given x they have. So keep in mind the condition is f at a and b is strictly greater than x, which means that we want to make sure x1 is strictly greater than or equal to x. And so that's like kind of how one condition works. But we know that because the sum of like all these elements in here never change, we know that a at 1 plus a at 2 plus a at 3 plus a at 4 has to equal to x at 1 plus this quantity plus this quantity plus this quantity. So if I just like, I'm just gonna condense this to 4 at x because, well, 4 at x1 because there's 4 x1s plus b at 1 plus b at 1 plus b at 2, I'll use parentheses like this, plus b at 1 plus b at 2 plus b at 3. We know that the sum has to equal to a at 1 plus a at 2 plus a at 3 plus a at 4. Okay? And so that's what this turns into. That's what this like process can give us over here. And so after like moving around some terms, well, okay, it might be better to define it like this, because you want to think of it like this is just a prefix sum of like array A, and this is some prefix, and this is like a prefix sum of prefixes, because B1, B1, B2, and B1, B2, B3 are all like prefixes of B, and this is essentially a prefix of those prefixes. And so that's like a nice way to visualize it. So in other words, if we have, after simplifying that equation, we have this. We have, let me think. So if it was a at I is equal to this, I probably shouldn't have erased that. But okay, it should be a at 1 plus a at 2 plus a at 3 plus a at 4. And then it should be, I believe, subtract. Wait, let me think. It should be equal to this, plus this, plus this, plus this. Yeah, it should be subtraction. So, and then like you subtract, like essentially the prefix of prefix sums of B. I want to define it as like PP at B. Well, actually, wait, no. Maybe I shouldn't do that. Okay, for this example, I'll just do it like this. I'll do minus 0 plus B at 1 plus B at 1 plus B at 2 plus B at 1 all the way to B at 3 plus B at 1 plus B at 2 all the way to B at 4. And then this will all get divided by 4. So this is like this value of x1 that we care about, and this is equal to f at a and b. So we know that given an array A and given an array B, f at a and b is going to be equal to this. And this is obviously generalized with 4 elements in the prefix, but we can like generalize this for all prefixes if we write this formula over here. Like f at a and b is going to be equal to a1 plus all the way to a at I minus like I'm gonna just write prefix of prefix sums of B. And then this is just like you have like I terms in here. And this is all over I. Like I'll just label prefix I of prefixes of B. So this is a general formula for what f of a and b will look like for considering some prefix of moves, like some moves done on a prefix of length I, with array I and array B over here. So this is a lot of information to take in, but we are almost there, I promise. All we need to do is to rearrange this equation slightly more. So I'm going to just call this term over here capital B. Over here, okay? Like capital B at I. That way it's not as messy as it is. So what we have now is we want to make sure f at a and b is greater than or equal to x, because that's the only time we want to count an array. So in other words, for a given I, we want a at 1 plus a at 2 plus all the way to array at I plus, or it's not plus, but minus. Is it minus? Yeah, it is minus. Minus capital B at I, all over I. We want it to be greater than or equal to capital X. So we can rearrange terms, and we have now that a1 plus a at 2 plus all the way at ai. So essentially the prefix sum of the prefix of length I, this quantity has to be greater than or equal to I times x plus b at I. And this is a condition that has to be held for all I if we want this array to to converge to a value that's greater than or equal to x. Whew, that was a lot of information. But if you see this problem now, you might think, wait a minute, the bounds on n are pretty small. N itself is at most 100, and all of the values, it gives like b at I, c at I, a at I, whatever, like all those values themselves never exceed 100 either. So you might be thinking, wait a minute, if all we need to do is to make sure that this condition is held for all I, in other words, like we have like some choice of like what prefix of moves we want to do on here, then this means that we can just do a DP. So we can do a DP like DP at I, where I is like, we consider the first I elements. And then this is equal to the sum of the entire prefix that we're considering, because we need a sum to check the validity to check whether like it's valid to have some array so that this condition is satisfied. And there's a sum of a at 1 all the way to a at I. And so this DP will use 100 times 100 squared memory, which is fine. But then you might think, or I mean, not might, you probably will think, well, if I want to do these DP transitions, how am I going to do this like quickly? Because if you just do it naively, then I believe it's something like 100 times 100 to the power of 4 operations, which is definitely going to not work in time. Well, what you can do is you can actually use prefix sums, because we know that dp at I only depends on dp at I minus 1, right? And just like some value, like whatever. We can take what this stuff in here and we can create prefix sums before we calculate these dp at I values. That way, when we like choose like some value of a at I, we know that the values that this dp state depends on in the dp at I minus 1 states forms some like segment in here. In this segment, we can just query all the sum of all of these dp values in here in O of 1 using prefix sums. So with that optimization, we solve the entire problem. And to summarize what this looks like, this is obviously 100 times 100 squared memory, which is about 1 million memory. And then this is going to be, with the prefix sum optimization, it's going to be about 100 times 100 squared time, which we can like quickly summarize to be like O of n times like m squared, where m is like the maximum value in all these arrays. So this is essentially just O of 10,000 times n, which is roughly 10 to the 6th, which is completely fine because we have 10 to the 6th time, and this is how much time it takes to solve one query of x. So keep in mind that this is the easy version of a problem. Like I said, this is like what, a 30-minute video by now, and I've only explained the easy version. But the good news is that the harder version of a problem uses all of these observations that I've already explained. So I actually haven't solved the hard version yet, but if you do want to give that a shot, then hopefully you have fun with that. I don't know what else to say, but yeah, that was a lot. That was really interesting. Yeah, so it's just like DP. Woo. This is probably my first time like trying to explain a pretty challenging problem, or like a really challenging problem, like to the point where I like start to have trouble solving it by myself. So if you found it confusing at all, then definitely check out the official editorial. And if you have any questions that you think I might be helpful for, then just leave them down in the comments below and I will try my best to get to them. I am very tired right now. I will probably go to bed because it is pretty late. But yeah, if you're doing this contest, then if you watch a video by now, then that means you've already done the contest. The reason why I'm not gonna like wait any longer. Yeah, peace.